You think you know why fire burns. Think again. You'll say chemical reaction. Maybe, if you're feeling more sophisticated, you'll mention oxidation. Carbon reacting with oxygen. Energy released as heat and light. And you know what's funny about that? You're right. Technically. But Richard Feynman, the man who won the Nobel Prize in Physics, who developed the most precise theory humanity has ever created to describe how light and matter interact, the man who was famous the world over for being able to explain anything in a way a 10-year-old could understand. Richard Feynman couldn't answer that question satisfactorily, and he knew it. In 1981, in an interview with the BBC, Feynman sat in front of the cameras and confessed something that haunts every honest physicist, that the more physics you learn, the harder it becomes to answer a simple why. In this video, we're going to descend through every layer that exists between you and the answer. Chemistry, atomic physics, quantum mechanics, the most precise theory in the history of science. And when you reach the bottom, you won't find an answer. You'll find something better. But before we get there, I need to tell you where Feynman came from. Feynman was born in 1918 in Queens, New York. He grew up with a father unlike most. Melville Feynman was not a scientist, but he had a specific way of teaching his son. Every time young Richard pointed at something and asked, "What's that?" his father would describe it, explain how it worked, and then ask back, "But do you know what it really is?" There was a bird that used to appear in the yard. Melville would say, "That bird has a name in English, another in Italian, another in Portuguese. But when you know all the names, you know nothing about the bird. You only know what people call it." Knowing the name of a thing is not understanding the thing. That distinction marked Feynman forever. He grew up distrusting answers that sound too good, distrusting explanations that satisfy the ego without illuminating reality. And then he became one of the greatest physicists of the 20th century. He worked on the Manhattan Project. He formulated quantum electrodynamics in the late 1940s. He received the Nobel Prize in 1965. He became famous for turning impossible things into something that seemed obvious once he finished speaking. And yet, when someone pointed to a fireplace and asked, "Feynman, why does fire burn?" he couldn't stop thinking. Not because he didn't know, but because he knew too much. There is a central paradox that will guide this entire video. The question, "Why does fire burn?" seems too simple to be interesting, but embedded within it is the most profound, fundamental physics the human mind has ever uncovered. And the more layers you peel back, the more you realize that each answer is not an arrival. It's a trapdoor that drops you into the next question. Feynman wasn't stuck because he was foolish. He was stuck because he was honest. Let's descend together. The first thing that needs to die is your mental image of fire. You probably picture fire as a thing, a substance, something that's just there, that you can see, that burns. You try to touch it, it hurts. You blow hard, it goes out. It makes sense to treat fire as something that exists in space. But fire is not a thing. Fire is an event. Before any chemistry, before any equation, fire is technically a plasma, the fourth state of matter. And this is where the ground disappears beneath your feet. You learned about solid, liquid, and gas. But there is a state beyond. The interior of the sun is plasma. Lightning during a storm is plasma. The flame of a simple candle, that quiet thing you use at a dinner, is technically plasma. When a gas is heated enough for electrons to escape their atoms, it becomes ionized. Nuclei and free electrons moving independently, colliding, recombining, emitting light in the process. That is what you call a flame. So right out of the gate, fire is not a thing. It's a process occurring in matter in a state most people don't even know exists. Now the answer, chemical reaction. It's not wrong, it's incomplete in a very specific way. When someone says fire is a chemical reaction, they're saying something technically true that explains absolutely nothing about the experience of fire. It's like saying a symphony concert is variations in air pressure. Correct. But so what? What is actually happening? Why does the process release heat? Why does it emit light? Why does the flame have color? There is a fundamental distinction that most people confuse without realizing it. Heat and temperature are not the same thing. Temperature is the average kinetic energy of particles in a substance, a measure of how agitated they are. Heat is the transfer of energy between systems. When fire burns you, it's not simply because it is hot, as though that were an inherent property of the flame. It's because energetic particles and photons are interacting with the molecules in your body and transferring energy directly into them. There is a crucial detail that is often overlooked. When combustion stops, fire simply ceases to exist. You cannot store fire in a box. You cannot pause a flame and restart it later. When the fuel runs out or the oxygen is exhausted, the process stops and the flame disappears. Fire was never a substance. It was the process itself, happening for as long as conditions allowed. This matters because it completely changes the nature of your original question. To understand this dynamic in depth, you need to investigate what is happening at each level of organization. It starts at the atomic level. To understand combustion, you need to understand what a chemical bond actually is, truly, not just the name. Imagine two atoms approaching each other. Each one has its positively charged nucleus and its negatively charged electrons moving around it. When those two atoms get close enough, the electrons can begin to be shared between both nuclei at the same time. Each electron is attracted to both nuclei simultaneously, and this distribution creates a state of equilibrium where the two atoms become locked together. That is a covalent bond. That is what holds molecules together. Chemical bonds store energy. The mechanism that makes combustion possible is fascinating. Breaking a bond requires energy. You need to supply energy to separate the atoms that were bonded together. But when you form a new bond, you release energy. The new configuration is more stable. The electrons are in lower energy states, and the difference has to go somewhere. Combustion is a process where you break some bonds and form others. The crucial trick is that the new bonds, specifically those that form carbon dioxide and water, are stronger, more stable, and sit at lower energy states than the original bonds of carbon, hydrogen, and oxygen in the reactants. When you burn wood, you are converting carbon and hydrogen plus oxygen into CO2 and H2O. The old bonds held a certain amount of energy. The new bonds hold less. The difference, for carbon, roughly 394 kilojoules per mole, has to go somewhere. It goes into the thermal motion of the product molecules, which is heat. And it goes into the emission of photons, which is light. But there is a detail worth pausing to think about. If combustion releases energy, why doesn't wood spontaneously catch fire in your living room right now? Because there is a barrier called activation energy. The molecules need to have enough energy for their bonds to begin breaking before the process can become self-sustaining. It is like a boulder at the top of an S-shaped hill. It is higher than where it will end up, but it still needs to be pushed a little upward before it can roll down. Once the temperature is high enough to overcome that barrier, combustion begins. At that moment, the process undergoes an irreversible turning point. The heat released by combustion immediately warms the surrounding reactants. Those reactants overcome their own barrier. They release more heat. That heat warms more reactants, which release more heat. Fire is not an instantaneous explosion. It is a slow-motion explosion that decided to keep the pace. Each molecule that burns provides the energy for the next one to burn. It is a chain reaction that feeds on itself as long as there is fuel. You just understood why fire spreads. Now the next question arises naturally. Electrons are moving to lower energy states. What does that mean? Why do electrons have specific, discrete energy states? Why can't they simply exist anywhere with any energy? That is where quantum physics comes in. In the early 20th century, Niels Bohr noticed something that seems absurd, but is completely verifiable. Electrons in an atom cannot have just any amount of energy they want. They only exist in discrete levels, specific orbitals with specific energies. There is no continuous gradient. There is no in-between. In the everyday world, there is no parallel for this. You can climb a staircase and stop between two steps. You can set a shower to any temperature, But electrons in an atom behave as though only the steps exist, and there is no space between them. An electron is either at one level or at another, never in between. When an electron receives enough energy from a collision, from an absorbed photon, it jumps to a higher level. But that excited state is unstable. The electron wants to return to the lower energy state. And when it does, the energy difference between the two levels must be conserved. It does not vanish. It is emitted as a photon, a single packet of light with energy exactly equal to the difference between the two levels. It is at this step that physics reveals its elegance. The energy of a photon determines its wavelength. High energy corresponds to a short wavelength, blue, violet, ultraviolet. Low energy corresponds to a long wavelength, red, infrared. Visible light photons fall between 400 and 700 nanometers in wavelength. This explains why flames have colors. A blue flame, the kind you see on gas stoves in complete combustion, burns at temperatures between 1,400 and 1,650 degrees Celsius. At that temperature, electrons undergo high-energy transitions, emitting short wavelength photons. A yellow or orange flame, the flame of a candle, of a bonfire, is cooler, around 1,000 degrees Celsius, and much of its glow comes from soot particles, fragments of carbon that did not fully oxidize and become incandescent, emitting lower energy light. But hot objects don't emit just one color. They emit a continuous spectrum based on their temperature. This is what we call blackbody radiation. The spectrum is so predictable and so precise that a physicist can look at the color of an incandescent object and determine its exact temperature without any thermometer. The color is the temperature. Temperature is the color. And the photons you feel as heat, that burning sensation when you get close to a fire without touching it, are infrared photons with wavelengths above 700 nanometers, invisible to your eyes, but with enough energy to cause vibrations in the molecules of your skin. When fire burns you, photons are literally bombarding the molecules of your tissue, transferring energy to them, increasing their molecular agitation to the point where cellular structures are damaged. Reflect on this for a moment. The light from a candle, that quiet flame you find beautiful, is made of falling electrons, cascades of electrons transitioning from excited orbitals to lower energy orbitals, each one emitting a packet of light in the process. Every photon that reaches your eye is the product of one single specific electronic transition, happening in a specific molecule at a specific position within the flame. Fire is quantum mechanics made visible. You are literally watching electrons fall. But another question arises. Why do electrons have these specific energy levels? What governs the orbital structures of atoms? What lies behind all this dance? The electrons, the bonds, the energies, the photons. The answer has a name, and that name is the reason Feynman's story is particularly ironic. There are four fundamental forces in the universe. The strong nuclear force, which holds protons and neutrons together inside the atomic nucleus. The weak nuclear force, responsible for certain types of radioactive decay. Gravity, which you know well, and electromagnetism. All of chemistry, absolutely all of it, is electromagnetism. The attraction between negative electrons and positive nuclei that keeps atoms stable, electromagnetism. The repulsion between two nuclei that determines bond distances, electromagnetism. Atomic orbitals, the specific shapes electrons occupy around nuclei, are determined by the equations of quantum electromagnetism. The discrete energy levels we just walked through, direct consequences of electromagnetism. The light emitted when electrons fall, electromagnetism. The heat transferred by photons, electromagnetism. This brings us back to our protagonist, because electromagnetism was precisely Richard Feynman's domain. In 1948, together with Shinichiro Tominaga and Julian Schwinger, Feynman developed quantum electrodynamics, QED. It is the most precise theory science has ever produced. QED's predictions agree with experimental measurements to more than 10 decimal places of precision. To put that in perspective, if you measured the distance from New York to Los Angeles with that precision, the error would be smaller than the diameter of a hydrogen atom. What does QED say about the electromagnetic force? That it is mediated by photons. Not visible light photons. Those are what we call real photons, with measurable energy that you can detect. QED describes the electromagnetic force in terms of virtual photons, ephemeral particles that exist for such brief intervals of time that quantum mechanics allows them to borrow energy from the vacuum, and then vanish before they can be directly detected. They exist only as force carriers. Feynman invented a way to visualize this. Feynman diagrams. Imagine two electrons approaching each other. You draw two electrons arriving from opposite sides. Between them, a wavy line, a virtual photon exchange between them. That single diagram represents the mathematical calculation of how the electrons interact. It looks like a doodle in a notebook. But that doodle allows you to calculate, to 10 decimal places of precision, how light and matter interact. And that is exactly this process, in a version billions of times more complex, happening inside a candle right now. What is combustion at the QED level? It is an immeasurable cascade of virtual photon exchanges, rearranging matter into lower energy configurations. Billions upon billions of quantum transactions per second, reshuffling electrons between nuclei, creating the CO2 and H2O molecules we call combustion products. What you point to as fire is, as described by the best theory we have, a region of space where quantum force exchanges are occurring at sufficient density and intensity to excite electrons and generate visible photon emission. Stop and consider the implications of this fact, because it holds the greatest irony of our journey. Richard Feynman received the Nobel Prize in 1965 for creating QED, the theory that describes more precisely than any other what fire really is, at the most fundamental level science can reach. The theory he built is the most complete answer that exists to the question, what is happening fundamentally when something burns? And that theory is his. And yet, when someone pointed to fire and asked why, he could not give a satisfying answer. The man who created the theory of fire could not answer the question about fire. This is not defeat. It is the structure of science. And Feynman explained this in 1981 in a way I have never forgotten. To fully understand this, we need to go down one more layer. Have you ever tried to undo a fire? QED describes what happens during combustion with extraordinary precision. But it doesn't tell you why combustion only happens in one direction, why you can ignite wood, but never unignite it, why time points only one way. For that, you need another layer. The answer is the second law of thermodynamics. In an isolated system, entropy always increases. It never spontaneously decreases. But what is entropy really? Not disorder. That shortcut creates more confusion than clarity. Entropy is the number of possible microstates compatible with a given macrostate. It's a statistical measure of how many different ways the particles of a system can be arranged and still look macroscopically the same. Think of it this way. A house of cards has very few configurations that still deserve the name house of cards, but it has billions of configurations that deserve the name pile of cards on the floor. Nature doesn't prefer the pile. It simply has far more opportunities to get there. Now imagine that with every atom in a log of wood. A log has highly organized structure, long, aligned cellulose polymers, specific molecules in specific positions. There is a very restricted number of atomic arrangements compatible with intact log of wood. When you burn that log, you convert those organized structures into billions of CO2 and H2O molecules dispersed through the air. Now you have molecules flying in random directions, able to occupy countless different positions and velocities. The number of microstates compatible with burned wood dispersed gases is astronomically larger. The universe doesn't forbid the log from being reconstructed. For the particles to spontaneously return to their original positions, they would need to have exactly the right velocities and directions all at the same time. A coincidence so improbable, it is effectively impossible, even if technically not forbidden. Now scale that up to the cosmos. The sun is converting hydrogen into helium, irreversibly, 4 million tons per second. Every star in the universe is doing the same, converting organized matter into higher entropy states, emitting radiation that scatters through the cosmos in every direction. Every galaxy you see in a telescope photograph is an entropy furnace. The entire universe is burning in this sense. Every irreversible process is entropy increasing. Every energy transformation is a step toward a state of maximum disorder. The fire in your fireplace and the death of stars are the same process. A child lighting a birthday candle and the final collapse of the sun are phenomena of the same physical family. Incomprehensibly different scales, same law. One fundamental gap remains, however. Why does the universe have this law? Why does entropy increase toward the future and not the past? Physics describes the behavior with extraordinary precision. The deeper why remains unanswered. And that is exactly the point Feynman wanted to make one afternoon in 1981. He was sitting in a chair in front of a BBC camera in a conversation that would be broadcast as "The Pleasure of Finding Things Out." And a friend asked what seemed like a simple question. Why do magnets repel each other? Feynman paused. And then, rather than answering, he began to explain why he couldn't give a satisfying answer. But to understand why Feynman responded that way, you need to understand what his father had planted in him decades earlier. Remember the bird in the backyard? Melville Feynman would point to a bird and say, "That bird is called this in English, something else in Italian, something different in Portuguese." But when you know all the names, you know nothing about the bird. You only know what people in different countries call it. Knowing the name of a thing is not the same as understanding the thing. Feynman spent his entire life taking that distinction seriously. And it was precisely that distinction which made the question about magnets impossible to answer satisfactorily. Because when you ask, why do magnets repel each other, you are asking for an explanation in terms of something you already accept. Feynman could explain magnetic fields, but then his friend would ask, why do magnetic fields repel each other? And Feynman would give Maxwell's equations. And his friend would ask, but why do Maxwell's equations work that way? And Feynman would arrive at QED. And in QED, the question becomes, why do virtual photons mediate the electromagnetic force in this specific way? And here the chain stops. The only honest answer is, because that is how the universe is built. As far as we can measure, as far as any experiment shows us, this is the behavior of reality. And the next question, why reality has this structure rather than another, has no available answer. Not because physics is incomplete, but because we have reached the frontier where science describes, and the question you want to ask lies on the other side of that frontier. Feynman didn't find this frustrating, and that is what set him apart from so many others. He found it profoundly beautiful, because it means the project of understanding the universe is inexhaustible. There is no point where you arrive and know everything. Every true answer opens the way to the next genuine question. The frontier never stops retreating. And every time it retreats, the territory you have gained is real, permanent, verifiable, extraordinarily useful. "I don't know" is the most scientific sentence a physicist can say. It is the only answer that keeps the door open instead of pretending it is closed. Feynman's father had taught him this with a bird. Feynman spent his entire life confirming it was true with the most advanced physics on the planet. Trace back the entire journey we've taken together. Fire is a plasma, a process, not a thing. Every layer we descended through, the chemistry, the quantum orbitals, QED, entropy, is genuine, real, verifiable. And each one opens the step below. Not because science failed, but because reality is too deep to have a bottom. The question, why does fire burn, is not a simple question with a complicated answer. It is a question that contains within itself the complete map of how physics works. 4 fundamental forces, quantum mechanics, thermodynamics, and the honest epistemology of where knowledge meets its limit. The child who points to a bonfire and asks why is asking the exact same question as Feynman. The difference is how many layers you can pass through before hitting the same wall. Feynman called it the pleasure of finding things out, the pleasure of discovering things, not of having discovered, of discovering. The present continuous is the key. The process is the point. The question is the map. If you now look at a flame differently than you did before this video began, if you see electrons falling, photons exchanged, entropy increasing, quantum mechanics unfolding right before your eyes, then you are already doing what Feynman did. You are descending. If you want to keep descending, this channel won't be ending anytime soon. The universe has infinite questions.